Select the major product of the following reaction. And we see over the reaction arrow, it's telling us that this is a Diels-Alder reaction. So let's recap what a Diels-Alder reaction is. So this is what we call a 4+2 cycloaddition reaction. And what this 4 and this 2 indicate is the pi systems that are coming together. So this is a 4 pi plus a 2 pi system. So that 4 pi is going to be a diene, and the 2 pi system is going to come from the dienophile. And so the diene is always a conjugated diene that can adopt this S-cis conformation like this. And so it is 4 pi electrons, 2 pi electrons in each of those pi bonds. And so I'm going to number that system. It's these 4 carbon atoms that are involved. And then the dienophile, the 2 pi system, can be an alkene. It needs to have at least 1 pi bond. You can also use an alkyne. And so those would be 5 and 6. So this is a cycloaddition reaction that brings together these 6 carbon atoms, and it's always going to form a 6-membered ring. And so we can draw our arrows. So this is indicating a bond forming between the carbon I've labeled 6 and carbon 1. And so that's going to push this pi bond in between carbons 2 and 3. And then we'll push this pi bond over to carbon 5. So what we're indicating here is that we are forming a 6-membered ring. And if we follow our flow of electrons, we see we've got a new single bond between carbons 1 and 6. So let's number these carbons. We have a pi bond between carbons 2 and 3. And we no longer have a pi bond between 3 and 4 because we shifted that pair of electrons from that bond to form the sigma bond between carbons 4 and 5. And so a Diels-Alder reaction will always undergo this pattern. So these 6 carbon atoms will always be undergoing this sort of cycloaddition reaction. And then any substituents that are attached to those carbon atoms will still be attached to them in the product. They're not involved, but those bonds are also not going to break, so they will still be there in your product. So we need to locate these 6 carbon atoms in what we were given. So we can see our conjugated diene. So we can number those as 1, 2, 3, and 4. And then we have our other 2 pi system here. We see an alkene. And where both of these are symmetrical, it doesn't matter where I label as 5 or which one I label as 6. So I'm just going to say 5 and 6. And so when you're drawing the product of this, and let's draw it up here, I always start by drawing the 6-membered ring framework because by definition, a Diels-Alder reaction will always give you this sort of framework. So I also need a pi bond. And that pi bond, if you follow this consistent numbering system all the time, will always be between carbons 2 and 3. Okay, and so now all we need to do to get to the right product is we need to make sure that anything that's attached to these carbon atoms is still attached to it, and anything that's attached to carbons 5 and 6 is still attached. So we can see that on carbons 1, 2, 3, and 4, between carbons 1 and 4, we have 2 carbon atoms. So there they are. So we want to make sure that in between carbons 1 and 4, we still have 2 carbon atoms. So 1, that's 2. So we'll keep them highlighted in the same color. So those are 2 carbon atoms. So this is a bridge between carbons 1 and 4. And it's not that we made a new bridge, it's just we had one already. They were already joined together and we didn't break those bonds, so they need to still be there. And then on carbons 5 and 6, each of them have this methyl ketone. And we also want to notice that this alkene is a transalkene. And we see that because we have 1 bond pointing up and 1 bond pointing down. So they're pointing in opposite directions. Okay. All right, and so we want to make sure we have 1 bond pointing up and 1 bond pointing down in what we have up here. So we can show that in our kind of flat structure by using dashes and wedges. So it doesn't matter which one we make up or down, because this could actually flip over. So we'll just make one up and one down. And we'll put our ketones on there. And now we need to look for that structure here. So we've got this 6-membered ring with a 2-carbon bridge, ketones pointing up and down. And so that looks like B. So if we were to straighten this out, this is a flat drawing. Whenever you put this bridge, it actually kind of puckers that ring. So I'll just quickly number here so we can also see that the structures are the same. So we see that 6-carbon atom ring. We see the 2 carbon atoms, 1, 2, that are in between carbons 1 and 4. And then we see that trans orientation of the substituents on 5 and 6. And that's coming from the fact that it was a trans bond. So we see one of those pointing up and one pointing down.